Physics chapter 26 theory video 2 current direction. Now this is actually the an extension of the what we have learned earlier. So we learned about Fleming's left hand rule. Now that was for the motor, for motor rule. We define it as motor rule. So now this is electromagnetic induction is the opposite of that. That is the mirror image of the motor effect. So here what we have is now in the motor effect what we had was current producing a force. Now current producing a force that was force was made on a current carrying conductor in a magnetic field. Now what happens is we provide an external force on a conductor which makes it move across the field, and that induces a current in the conductor. So this is actually the mirror image of the left hand rule, and we call it the Fleming's right hand generator rule. So the two definitions are different from one another. In the first one, in the Fleming's left hand motor rule, what happened was the current produced the force. Here what happens is the force produces a current. So this is the right hand rule. So you have to remember Fleming's right hand generator rule. So when you have your right hand facing your face, the thumb and the palm should be facing your face, and then thumb, first finger and second finger, they should be at right angles to each other. So this is something that I have been taught previously, even in O levels. So take your hand and direct the three fingers in either direction, so that it is the angle is 90 degrees from one another. Once again, the three fingers will represent the same thing. Thumb will give you the direction of the motion, and the first finger gives you the magnetic field. First F stands for magnetic field. Second finger gives you the conventional current caused by the induced EMF, and please remember that is a conventional current. So you know that it is talking about the positive charge movement. So in this particular situation here, a conductor is moved downward across the magnetic field, then the current is flowing in the direction that is given by the red arrow. So as a result, you can figure out one of the three if two of them are given. Then you can find out the direction of the current if the field and the motion is given, or else if the one of the three can be found if the other two are given. Then we go to induced EMF, but before that let's write down this note: current direction in Fleming's left hand motor rule. In Fleming's left hand motor rule, a force was generated on a current carrying conductor in a magnetic field, but in electromagnetic induction, a current is caused by induced EMF when the conductor is moving through a magnetic field. As a result, The rule applied here is the mirror image of Fleming's left hand rule. Leave a line and write. In electromagnetic induction, we use Fleming's right hand generator rule to find the direction of the current. And please draw this diagram and write what they represent. Thumb, direction of motion; first finger, direction of external magnetic field; and second finger, direction of conventional current. So you can, if you want, you can draw this also, figure 26.9 also, to make it clearer. But if you have understood, then you can move on. So now let's try to learn a little bit more about the induced EMF. If the conductor is not a part of a complete circuit, we can't have a current flowing due to the EMF. So, but still, there will be an EMF. As a result, there would be a negative charge that accumulates at one end of the conductor. So, as a result, the other end becomes positively charged. So, as a result, there is an EMF that is induced at the ends of across the ends of the conductor. So now there is a problem that comes because there is a charge, difference in charge. So it could be considered as the potential difference or voltage. So now we have to understand the similarities and differences between or the distinction between voltage and EMF. In this particular situation, we have to use the term EMF because there is work being done when we push the wire through the magnetic field, and that is converted into electrical energy. Because we have not connected the ends together, because we have not connected the ends to an electrical instrument or something like that, this is simply a source of electrical energy. The source of electrical energy is not potential difference, because just like the battery, when we talk about a battery, we talk about the EMF, electromotive force. So it has, so the correct term is obviously EMF, because it is a source of electrical energy. Now we go to this diagram, how we induce the EMF across the ends of the conductor. When there is a wire, when there is a this part, this conductor, when it is placed in this magnetic field and when it is moved, what happens is, now it is not connected into a circuit. When we do that, we know that there is because the direction of the current, right? Because of the direction of the current, you have to take the positive charge accumulating at one point and the negative charge accumulating at the other. So this movement, so as you can see here, so the current flows in this direction. So that means the current is flowing in this direction, motion is downwards, and the field is in the direction that is given by the blue arrow. So in this way, we know that the charges get accumulated at either end. Now what happens is, how this is explained is, the conventional current is from negative to positive, because within the conductor, in this conductor, the conventional current is from negative to positive, just like inside a battery or any form of EMF. So we know that free electrons within the conductor will travel from right to left. That is, we know that it has to be, the reason why this becomes positive is because electrons have traveled. Electrons have traveled from right to left. I hope that makes sense. Making the left hand side of the conductor negative. So that is the reason why it has become negative. So the electrons have moved from right to the left. So this is after this is actually this diagram represents after the EMF has been built up. So now moving the conductor, so now after you connect it to some other material, then the electrons would flow back from the negative to positive. The electrons would flow from negative to positive. That is actually the real flow of electrons, right? But here we are talking about the EMF that is being developed. So now what happens or what causes these electrons to move? When we move the conductor, what happens is we give a free electron inside this conductor a velocity in the direction of its motion. And this electron experiences that magnetic force BeV due to the movement in the magnetic field, and that goes from right to left. That goes from right to left. So that is the reason why it moves across. Write down a note. When the conductor does not make a part of a complete circuit, a current cannot flow. However, an EMF is induced, making one end of the conductor become positively charged and the other end negatively charged. Because in effect, this becomes a source of electrical energy, we use the term EMF rather than potential difference. As shown in the below diagram, within the conductor, conventional current moves from negative to positive, just as in any other source of EMF. The magnetic force BeV, capital B, simple E, simple V, makes the electrons to move from right to left, leaving the left negatively charged and the right deficient of electrons and positively charged. Leave a line, put a star and write down. When this is connected to a circuit, the electrons will flow from negative to positive. And please draw figure 26.10 so that you would understand it better, and then answer questions 2 and 3.